Swayam Prabha. Digital India. Educated India.
Welcome to Module 49 of Point-Set-Topology course Part 1. Last time we introduced the notion of Hausdorff spaces and proved some very important theorems. One of them was a characterization of homeomorphisms. Characterization means in a particular cases, that's all. Namely, if you have a bijection from a compact space to a Hausdorff space, then it is a homeomorphism. So there are other cases also that we have proved. So let us try to give some illustrations of usefulness of these concepts and theorems. So we go back to the study of quotient spaces now. Let X be a topological space and J be any interval of the form A, B closed or A closed and B open. And B could be infinity also. Okay, so I will, instead of writing AB and so on, I will just write it as J. It will represent any one of them. By a cone over J, we mean the quotient space of X cross J by the identification X comma A is identified with X prime comma A for every X and X prime inside X. And no other identification. That is the meaning of when you define a relation by declaring some rule. The rule is only this one. After that, by reflexivity, transitivity, symmetry, etc., the relation is completed. Okay, as an equivalence relation. So in this case, by reflexivity, every point is connected. That you have to take it as a definition. It's not there. Symmetry is already there here. And transitivity is also obvious. So only points X cross singleton A, they are identified to a single point, a single class here. Okay. So that is the meaning of this cone over X. The quotient space will be denoted by Cx. Okay. So the image of X cross A under the quotient map is called the apex of the cone. Okay, what single point it is, the entire X cross 0. So that will be called apex of the cone. The image of X cross T for any T not equal to A. See, there is a point other than A. They are all as it is, as they are. There is no identification. So X cross T to its image is a homeomorphic copy of X. Okay, and it will be contained inside the cone. Under the quotient map, it is again a homeomorphism, and this may be selected to be called the base of Cx. Why I am saying selected to be? Because there is no definiteness. You could have taken any T other than A. So all of them you can say that is the base of the cone. In practice, especially when J is a closed interval, we can take T equal to B. Okay, we select X cross B as the base. So there is a definiteness. Okay, in the case of open cones, namely when be open or be infinity, and then also it is open anyway, there is no definiteness. So there is also these terminologies, open cone and closed cone, depending upon whether you have taken a closed interval here or an open interval. Not an open interval, half open interval, JAB. JAB corresponds to this A comma B, B open will correspond to open cone. An open cone doesn't have a unique base. You could have taken any T, they are all equal. They are serve the same purpose. Whereas in the closed cone, you can take the last point here, B, then X cross B will be the base. The prototype of this one is when X itself is a circle. Then you must have seen all the pictures of right circular cone and so on. In 12th standard, you study the cones also. Okay, conic sections and so on. So the definition is generalized from, instead of X being circle, you can take any topological space and do this. Okay, so cone construction is one of the very, very important thing especially in algebraic topology, also in topology. Okay, it has some canonical properties which we shall describe. What is the meaning of this canonical property? Suppose you have a function from x to y, okay, any function. Then you can define CF from Cx to Cy. So you have defined the cone over a space. Now I am defining the cone over a function here, cone of CF. So what is CF? CF is a map from Cx to Cy. First you define it from x cross j to y cross j to be f of xt equal to fx comma t, and then they take the class. Okay, here also you take the class cf of xt going to fx comma t. Remember, this class is the same point xt unless t is the first point a, and when it is first point a, all these xt represent the same point. But here also they will represent the same point. So there is no problem here in the definition of this function CF. Okay. The point is, if f is continuous, then f cross identity continuous, then the induced map CF, this will be also continuous. Not only that, there are many other properties. I want to list them. The CF has problems. So, how the following properties? If f is continuous, then so is CF. If you start with the identity map from x to x, C of the identity is identity of Cx. If you have x to y and g from y to z, then the cone over G composite F is nothing but cone over G composite cone over F. If F is a homeomorphism, then so is CF. Okay. So 1, 2, 3 are all easy. The 4 follows from 3 by taking f from x to y and g equal to f inverse. If you put f inverse from y to x, then C of G composite F is its identity. So that is identity on this side also, which means CG is the inverse of CF. Therefore, CF will be homeomorphism. Okay. So these things are easy to verify. There is no problem about them. Okay, these are called canonical properties. Now I will come to specific examples. Suppose you start with S0, that is the zero-dimensional sphere, which is just unit vectors, unit numbers inside R. It's -1 and +1. The topology is discrete topology on that. What will be the cone over that? to be very specific now, I take j equal to the closed interval 0 to 1. Okay, what will be the cone of S naught? It's easy to see that. First you take S naught cross j. So that will consist of 2 copies of the interval, closed interval 0, 1. 0, 1, minus 1 cross 0, 1 and plus 1 cross 0, 1. They will be disjoint copies, right? But when you identify which one, what is the identification? I have to take A to be minus 1 here, right? A to be 0 here, right? So minus 1, all the points, minus 1 plus 1, cross 0, they will be identified. Nothing else. That means what? The bottom points of both these arcs 0, 1. 0, 1 is the arc. You hold them vertically. Okay. So minus 1 copy is there, plus 1 copy is there. Those minus 1 and plus 1 cross 0, 0, they will come together. So you will get a V shape, right? But V shape is homeomorphic to minus 1 plus 1 closed interval from minus 1 to plus 1. Okay. So this is the very simplest case. As such, I have already told you that if you take S1 as a circle, then the cone over that one will look like actually an ice cream cone or a funnel and so on. Okay, if you flatten it out, what you get is a disk, the two-dimensional disk. So that point I will explain a little more clearly and in more generality for all n. So more generally, put x equal to Sn minus 1. So n equal to 2, this will be just the circle, but I am now considering general case together, all of them together. N equal to 1 is over. And j equal to 0 to infinity. Instead of the closed interval, I take 0 to infinity. Consider the map eta from x cross j to Rn given by eta xt goes to t times x. So this is a unit vector. I am multiplying by a scalar. The scalar varies from 0 to infinity. Clearly, this multiplication map is a continuous surjection. Every point inside Rn, okay, take a vector, divide by its norm, that will be a unit vector. That will be inside Sn minus 1. What is the corresponding t? It's just the norm. You multiply it by the norm, you get back the vector v. Okay, so this is surjective map. Okay, it is a bijection if you take non-zero vectors and don't take t equal to 0. That means on the open interval 0 to infinity cross x, it's a bijection. Okay. And where does it go image? Image is Rn minus 0. Okay. So this is precisely what you call as polar coordinates in the case of n equal to 2. At 0, 0 comma any vector v, that will represent 0 into v, which is just 0. So that point is over-represented. Okay, there are too many points which represent that point. But everywhere else, there are unique representations. So eta of x0 is 0 for all x in x. And hence eta induces a continuous bijection when you pass on to the cone. See, whatever eta was taking several points to same point, all those several points, various points, namely x, 0, they are all identified in Cx to single point. Therefore, the eta hat from Cx to Rn, this is injective map also. It is already surjective. This eta is surjective, so eta hat is also surjective. So this is a bijection. Okay, it's a continuous bijection by the very definition of how to check continuity on quotient spaces. Because eta is continuous, so if you write Q as x cross j to Cx as your quotient map, so eta hat composite Q is eta. So it's continuous means eta is continuous. Okay, so eta hat composite Q is eta. Q is the quotient map. That's what I have. I am denoting this one. Okay. So why this is a homeomorphism? Right? If you knew that this is compact, this it's Hausdorff, then you are done. Right? In particular, instead of taking infinity here, suppose I take a closed interval, 0 to 1, 0 to a, whatever a positive. Okay, then I would get a homeomorphism, but I will not get on to Rn. What I will get? Suppose I take this one, it's 1. Then I get all vectors of length less than or equal to 1, which is nothing but dn. If I take R here, I get all vectors of length less than or equal to R, which is the closed ball BR0. Right? So our theorem already says that all these balls are cones over what are the bases there? What is the last thing when the second coordinate is equal to R? That will be the sphere of different radius, not Sn minus 1. Sn minus 1 you get only when R equal to 1. Okay. I want to say that even this infinite cone Cx is homeomorphic to the entire Rn. Okay. So there are different ways of seeing this one. The point is continuity of the inverse, this part. Okay. If you throw away the 0 from the 0 from here, 0 from here, that is obvious because there it is eta xt equal to tx unique. So how do you get xt? You see, it is just the first coordinate is x, whatever v divided by norm v, the second coordinate is norm v. So both of them are continuous there. I can divide by norm v because v is a non-zero vector. But if it's a zero vector, you can't do that. So there is a doubt when you extend it to Cx, why this is continuous. Okay, sorry, this continuity is okay. Why the inverse is continuous? There is no justification there. Okay, so let us prove that one rigorously once for all so that you won't have any doubt left in your mind. So we claim that eta has a homeomorphism. For this, we need to check eta hat is an open mapping or a closed mapping. Okay, let U be an open subset of Cx. Okay, put V equal to Q inverse of U. See, I start with a subset here, but then I go to Q inverse of that. I am coming to x cross 0 infinity. Okay, closed interval 0 infinity. Here I am coming. Okay, that is my V equal to Q inverse of U. We make two cases. Suppose the apex point x cross 0 is not in U. That just means that V is completely contained inside x cross open interval 0 infinity and Q from V to U is a homeomorphism. This case is very easy. This we have already analyzed. Since x cross 0 infinity to Rn minus 0 eta is a homeomorphism, eta V is open. Okay, and in this case eta V is same thing as eta hat of U. Okay, so this part is okay. Second case is the important case, namely suppose x cross 0 the apex point is inside U. The singleton x cross 0 is a closed subset of Cx. Okay? Why? Because the rest of them is open. That is easy to see. Or inverse image of x cross 0 is just x cross 0, the entire set. Something is open, something is closed. If you notice, the inverse image is closed, right? So x cross 0 singleton is closed. Q inverse of that is x cross 0. So that is closed, so this is closed. Therefore, it suffices to show that eta u is a neighborhood of 0 in Rn. This point is coming to that point, right? So rest of them is no problem. So its only problem is why it is a neighborhood of this x cross 0. Okay, it's a neighborhood of 0 in Rn. We now use the compactness of x equal to Sn minus 1 and Valle's theorem to get an epsilon positive such that this W is equal to x cross 0 epsilon, okay, is contained inside V. See, you have a x is Sn minus 1, which is compact. Cross 0 to infinity you have. Okay, so this is your y, and then use Valle's theorem. If you have an open subset containing x cross some little y, then you have a neighborhood V. Okay, if you have neighborhood V, then you have a neighborhood of, what is this? An ball, F0, epsilon ball here, such that this x cross 0 epsilon is contained inside V. Okay, x cross 0 is contained inside V, which gives you a small epsilon. So this is the Valle's theorem applied to x equal to Sn minus 1. Okay. Under eta, the image of W is nothing but the open ball B epsilon 0. This is a unit vector. I am multiplying it by some number between 0 and epsilon. So it will give you a vector of length less than or equal to epsilon, less than epsilon. All vector less than epsilon are inside this one. So this is an open ball. Image of this one is open ball, which is clearly contained inside eta V, which is eta hat of V. Okay. So once it is inside V, eta of that one will be contained inside V, which is eta hat of V. So starting with an open subset U inside Cx, we have shown that eta hat of that is open. Okay. So open bijective continuous map is a homeomorphism. So I am making this remark which I have already told you. Yeah.
Would you please explain it again how Valle's theorem is applied there?
Valle's theorem, you have to remember what is Valle's theorem. If you have a topological space X which is compact and any other space Y, okay, then you look at X cross singleton Y inside X cross Y. Suppose it is contained in some open subset V. X cross little y contained inside V. Okay. Then there is a neighborhood of this y. Okay. One single neighborhood of this y such that X cross U is contained inside V.
Yeah, so here that neighborhood is 0 to
Zero epsilon, because it is 0 to infinity. This space y here I am implying to 0 to infinity. 0 closed, open, infinity open. So how do you get a neighborhood? Whatever neighborhood of 0, they will contain 0 epsilon. Okay?
Yes.
So I have already told you that when n equal to 2, this is the popular representation of R2 or complex numbers in polar coordinates. Unit vector in the complex numbers, you can write it as e power 2 pi it. But if you R3, R4 and so on, you can't write that way. You just write a unit vector. So then this is also polar coordinates inside Rn. Every non-zero vector is uniquely written as what? V equal to t comma u, where u is a unit vector. What is this u? This u is nothing but v by norm v. What is t? It is norm v. As soon as the vector v is 0, you have to take t equal to 0, but u could be anything. So that much of ambiguity is there in polar coordinates. But if you think of this as a cone, there is no ambiguity. Now, I want to do one more serious thing here. The above discussion is valid verbatim in any finite dimensional non-linear space M, norm. So we are doing it in Rn, but the same thing holds for every non-linear space which is finite dimensional. Okay, where we replace x by the unit sphere in M with respect to the norm. If the norm is L2 norm, you will get the U standard sphere. If it is L1, what you get? You get a diamond shape. If it's L infinity, you get a square and so on, right? So all these things we have seen. Even if it's arbitrary any norm, none of these LPs, this statement is true is what I am claiming. What is the missing part? The only missing part is that perhaps is why x is compact. X is what? Unit sphere. Why x is compact? Because, okay, M is finite dimensional. We want to say that x is compact. So I will, we might have already seen this one, but I will complete this argument. First of all, recall that by elementary linear algebra, it follows that any finite dimensional linear space is isomorphic to some Rn, where n is the dimension. Also, we have proved that any two norms on Rn are similar. Okay, similarity preserves boundedness and closedness. Therefore, this norm, whatever norm, I don't know, is the unit sphere with respect to this norm is closed and bounded subset with the L2 norm also. All right. In the L2 norm, closed and bounded subsets by Heine-Borel theorem is compact. So there is nothing missing. There was an apparently missing information, but everything is available. Therefore, what we have is that whatever analysis we did, namely C of x is homeomorphic to the whole of Rn, that is valid inside any nonlinear space, finite dimensional nonlinear space. Now we come to the converse of this one, namely, if the sphere is compact in a nonlinear space, okay, then what? Then M itself is finite dimensional. So that is the next theorem that we are going to prove. This is a standard result in function analysis. Okay. So let us prove this one as an application of whatever we have done so far. A nonlinear space M, norm is finite dimensional if and only if the unit sphere in it is compact. So let us denote by S the unit sphere. Suppose it is compact. Then you can take half balls of radius half around each point, that will be an open cover. So that should admit a finite cover. So there will be finitely many points x1, x2, xn inside S, such that S is contained inside union of all the balls of radius of center at xi, I into 1 to k. I have got some points inside a vector space M. So I can take the linear span of them, right? Let L be the linear span of x1, x2, xn. So this is a linear subspace of M. We want to claim that L is equal to M. If we prove this one, then it follows that M is finite dimensional. Dimension may be equal to n or less because these may not be independent. They span L. So dimension will be less than equal to n. Okay. So why L is equal to M? So the proof here is very important. The step. I won't have much time to spend on that one, but in functional analysis, they do much more elaborately about first order, quadratic approximations and so on. So all those things will be easy for you once you learn what is going on here. Namely, suppose you have a proper subspace. This part itself is an independent thing now. Suppose L is not equal to M. That's L is a proper subspace. Okay. Say X is in the complement of L. I want to find the nearest point to X inside L. So that is the approximation, nearest point. Okay. So I don't want to elaborate that one. So what we want to do is, L being a finite dimensional, okay, this is a complete and a closed subspace of M. This part we have seen. Okay, every finite dimensional nonlinear space is complete. Once it is complete, it will be automatically a closed subspace of M. So consider the function, the distance function, given by the same norm, nothing else. From L to R, given by distance of y, and d of y is distance of y with from x. X is fixed. So this is a continuous function. It's just equal to norm of x minus 1. Okay. Take d to be the infimum of all these dxy's where y ranges over L. Okay. So infimum, y infimum makes sense. First of all, see, the distance to some point is already finite, so that is fine, right? So they are all bounded, fine. So this non-empty and so on. So and distance function is always bounded below. Okay, so infimum makes sense. Why infimum is positive? If the distance is 0, okay, then we know that X will be inside L because L is closed. So distance must be positive. Okay. So this D, which is infimum of dxy, is actually the distance of X from L. Okay, I have just recalled this one here. So that is positive because L is closed and X is outside L. So then there exists a sequence yn inside L, okay, such that distance between x, y, n converges to D. What is D? D is infimum. By the definition of infimum, you must have points here converging to that point, right? So those points are nothing but D of x, y, n. They are real numbers. D of x, y, n converges to D. Okay. It follows that yn is a Cauchy sequence. See, dx, yn converges. These are real numbers, but this implies yn is a Cauchy sequence. Okay. But yns are inside L, which is complete. So yn converges to some y0 belonging to L. This y0 is the one which realizes this distance. It follows that D equal to D of x, y0. The limit will be D. t equal to dxy naught. Okay, when you take the limit, yn comes to y. So infimum is actually minimum and it is attained. All right. So in fact, now you see that this y naught in as such may not be unique in general, but in this case, because L is a linear space, it happens to be unique also, but we are not interested in that part. So we have got a point such that d equal to dxy naught, which is the infimum. So here the picture. So what I have taken, this is L. I am assuming that it is smaller than the whole space M. It is not the whole space. This is the origin. Okay. This is some ball of maybe positive radius, whatever. All right. This is my X. And on L, I have located Y naught. So these are Y1, Y2, Yn converging to Y naught. Okay, it turns out to be, if you know what is the meaning of perpendicular and so on, it happens to be like that. But this happens only in an inner product space. If you have just a nonlinear space, you don't have the notion of angle. So there is nothing like perpendicular and so on. So you don't have to draw these pictures perpendicular and so on. Okay, to be very precise. But what you can do is, you look at x minus y naught. That is the positive, that is the non-zero vector, right? You divide by its norm. That will be a point here on the unit sphere. Okay, so this z is nothing but x minus y naught divided by its norm. Okay, so that will be a point of the unit sphere. So this is what I am doing here. Okay, so next slide. Put z equal to x minus y naught divided by norm. Then norm of z is 1. Therefore, z is one of the b1 by 2 x's. Right? It must be in one of the b1 by 2 x's because the entire of the sphere S is covered by these balls for some I equal to 1 to up to k. Also, for any y in L, we have norm of z minus y. You can rewrite it as z is x minus y naught divided by norm of x minus y naught, right? So I am pulling x minus y naught is here, but I am pulling out the denominator outside. Okay. Then I have to multiply by that number x minus y naught times y. But now y minus this one is a linear combination of y naught and y. Y naught as well as y are inside L. So this whole thing is inside L, right? X minus y naught plus this thing. So that is an element of capital L. Therefore, this norm minus this one must be bigger than or equal to d. And then divide by this numerator, the denominator is there. D divided by norm of x minus y naught. Okay. So that's equal to 1 because d is nothing but the norm of d is equal to norm of x minus y naught. Distance between x and y naught. Okay. So what we have shown is that for every point y, the distance between z and y is inside L, is bigger than or equal to 1. So that is the absurdity because all these xi's are inside y, right? We have chosen those things inside y. So that is the problem. So that is why this picture is funny because it is absurd picture. So this ball should contain, one of these balls should contain z, but they are all of half radius. But this is at the this z is away from that. Okay, so this is the contradiction. So that contradiction because it's not the whole space. So once again, this method of minimizing this norm, etc., is important in elsewhere, but we have used it to prove that compactness of the unit sphere implies that the norm in space is finite dimensional. Okay? So next time we will continue with applications of this nature. Okay, more and more examples we will study. Thank you.